All right. Good afternoon, everybody. Welcome to the April already meeting of the Columbus Data Science Meetup, one of our new virtual meetups. Thank you all for joining, for attending. Today we have Hannes Hopke and Joe Pugh. Hannes and Joe are both at a fintech startup called Digits. Here, Hannes is a machine learning engineer. Previously, he was also at oh my gosh, Hannes, I'm so sorry. I'm forgetting your prior companies. I didn't. I thought I was gonna
SAP.
remember, but all right, that's on me. I apologize.
No
Um,
worries, no worries. All good.
in other news, at least. Oh, sorry. Go for it.
No, I worked at SAP, just if that's important, but sorry.
All right, that's completely my bad. I apologize. Hannes is also a Google developer expert and has co-authored two machine learning publications, NLP in Action by Manning Publications and Building Machine Learning Pipelines by O'Reilly Media. At Digits, currently he focuses on ML engineering and applies his experience in NLP to advance the understanding of financial transactions. Joe is also an engineer at Digits, where she focuses on data engineering and infrastructure. Prior to joining, she helped design and build the experimentation infrastructure for embedded tweets at Twitter, developed for the mobile developer platform at Fabric, now part of Google, and built self-service analytics and data pipeline tools at Yammer, formerly Yammer, now part of Microsoft. So with that, I'll turn it over to Hannes and Joe to kick us off. Thank you both.
Thank you, Christopher. Thanks for having us. Hi, everybody. Today, we would like to tell you how we do machine learning at Digits. We hope to provide you some insights of what we do besides training machine learning models. We want to talk about what do we do before we train a machine learning model and what we do afterwards. And with that, we already passed the intros. I'm super excited to be at Digits, where I can apply the two of my key interests is like natural language processing and machine learning engineering. And I have the great opportunity to work with Joe. And
Hello, everyone. I'm super excited to be here to talk about how we do ML at Digits. As Christopher introduced, I currently focus on engineering and ML infrastructure stuff at Digits, work a lot with Hannes. So you might be wondering, what is Digits, this fintech startup? So we are a real-time finance platform, for modern businesses. So at the core of Digits, here you can see like a CPU analogy. We're really ingesting your financial data from your banks or accounting software, and we strive to deliver the real-time insights that's driven by machine learning. Previously, you may get that insights a few weeks or months later from some legacy accounting software or through back and forth email exchange with your accountant. So we're trying to do that in real time, driven by machine learning. So to give you a couple of ideas on what we work on in the ML realm, so we do deep learning generated embeddings, named entity recognition, and various classification problems here at Digits. And today we're just going to give you an overview of how we do ML at Digits, and we will have time at the end for any specific questions you may have for us. So we are a very small team after all. We just need to heavily focus on automating the ML engineering process so that we can onboard new engineers and data scientists to new projects and really shorten the lifetime from a concept to production and make sure everyone is productive and we can continue to deliver customer values. So on the next slide, so here, in today's talk, we're actually going to talk about what happens to your trained models before and after when you're training. So there's a lot of talk that's focused on how to train a model, but that's not going to be our topic today. So at the center of ML operations, there is your ML code. There's actually a lot of things just surrounding your ML code to consider when you want to deploy a model to production. So as a small company like Digits, it is absolutely critical that we have a streamlined process for operating ML models so that we can churn out new models in a repeatable, reproducible, and scalable way. On the next slide, we would like to talk about. So after we experimented with our ML models in your Jupyter notebooks and what happens to your prototype. So of course, we would like to first come up with an idea and probably prototype something in your Jupyter notebook and show it to your teammates and stakeholders. And once we have confidence in the model, we would focus on bringing this model online. So when we do that, we really want to focus on making sure the model is repeatable, reproducible, and it's easy to trace bugs via audit trails so that when problems do occur when they're live in production, we can debug them easily. And then next, here is a picture of a very meticulous industrial designer really carefully crafting a car body using modeling clay. So you may argue that this car looks beautiful, but would you actually want to buy this car? Would you even I bet it's not even drivable. So you might want a coffee just from like a single origin and handcrafted artisanally by a person, but you probably don't want to get a car from a workshop this way. Instead, I would bet that what you really want is to buy a car from mass produced from this production line, where it's like streamlined process and there are parts that are easily replaceable and it's easy to track down problems in this production line. I would get a car from here. And then on the next slide, so the real world story is most machine learning models don't ever get deployed. Here's a quote from a Strava data conference a few years ago, saying it's been 11 months and my model still hasn't got deployed, even though it only took me 3 weeks to develop. So this is probably the truth for a lot of enterprise machine learning. But when your model finally see the light and get to meet your customers, when they do get deployed, they are also going to face a lot of challenges, as you can see on the next slide. So your model will experience maybe how your customer perceive this feature will change. They will experience data drift, and your engineering team might change the data schema around it, and how the data processing step, pre-processing step that you use in model training may be different from actually how this is done in your production code when that model is serving production traffic. And when you're attempting to predict for a large volume of data, if that model serving API endpoint couldn't handle that large volume, it may never get to finish because of the high latency there. And in today's talk, so we're just gonna talk to you about how we solve these problems at Digits. So everything absolutely starts with data, and data is the center of it. So here's a slide that shows a wide range of tools we use for data engineering here. So the core things that we use is Beam, Apache Beam, which is an open source SDK for parallel data processing. And it's distributed backend called Dataflow, which runs on Google Cloud Platform. So with these two tools, we actually, this probably covers most of the stack that we use for data processing at Digits. Again, we use Spanner for relational database. We use BigQuery as a data repository. Of course, we use Jupyter notebooks for prototyping ideas. Once that idea is solid and we would like to take it live, we would use TensorFlow extended for ML pipelines, and Hannes is going to talk at length about TFX later. And when we want to finally serve that model, we use TensorFlow serving to deploy it and serve it through a gRPC API endpoint. So next slide. I want to talk about the ETL process for data collection and feature extraction we do at Digits. So it uses the same data processing stack. So it uses Beam on Dataflow. Here, basically, we have our event logs and we have our relational database. So we design an ETL system that runs on Beam and Dataflow that pulls this information. It does a traditional ETL, it transforms the data and finally load them into our data repository. So this way, we actually build a very reliable snapshot of our features, which serves as a lightweight feature store. So in case we want to reproduce the model in a reliable way, we can go back to a specific point in time and do that. So we also build an in-house scheduling and dependency management system. So this ensures that the data snapshot that lands in our data repository is always fresh and use the latest data. So on the next few slides, I want to talk about some specific ETL techniques that we do that may seem very simple and straightforward, but actually save us a lot of time when we want to ensure like the model integrity and debugging model bugs. So the first one that's shown in the SQL query on the right hand side here is the technique that we do to produce a balanced data set. So in this example, we have a limited amount of positive examples, whereas the negative examples are abundant. So we just use a trick here that label every row in the negative examples data set with a row number. And ensures that we pick exactly the same amount of negative and positive examples and scramble them together to put together our training data set. On the next slide, I want to introduce to you how we do data splitting here. So we use a consistent hashing algorithm. So on our UUID, which stands for unique identifier. So that's a 128-bit hexadecimal string. So here's the technique shown to utilize that first 8 character to convert it into an integer and mod it by 10. So this will reliably allocate the same 10% of your whole data set just for testing. So this ensures that there's no cross-contamination between your training data set and test data set. It ensures that your model won't be overfitted to memorize on the same data. Cool. So after all this, we have our data that's ready for training, and Hannes is going to talk to you about how they flow through the model lifecycle.
As Joe said, data is front and center at Digits, and we build our machine learning models on top of our data repositories. And each model version we produce goes through a life cycle. So basically, we ingest the data, we do some data versioning, then perform some data validation, which is in that case model specific, do some data pre-processing, which is also model specific, and then do our model training. Once we have a trained model, maybe after a little bit of tuning, we then perform a model analysis where we check the model itself, and we do a model validation where we compare our exported model against previous exported model versions. And then once everything checks out and is looking good, we deploy our machine learning model through another process. But basically, in our pipelines, we push our machine learning models into a repository where we then would evaluate them one last time before we push out another automated process to deploy the model versions. And once the models are out in production, we then capture customer feedback or user feedback, and that generates more data for our machine learning models, so for our data sets. And then basically, we can kick off another model version run and produce another version after a day, a week, a month, whatever time frame we like. This process looks very linear, but in fact, it is actually very entangled. Each processing step uses various steps upstream to be used. It's not like a standard CI/CD system where you have sort of like the output of the previous step is the input to the next step. We're using here like maybe the output of the first step together with the output of the third step is the input to the fifth step. So they're highly entangled. If we would write this from hand, it would be fairly complex and the code would probably be really brittle. One way we abstract those complexities is by using TensorFlow Extended. TensorFlow Extended allows us to write in Python code our pipeline definitions, and then we can convert them to any orchestration tool we like, whether it's Kubeflow Pipelines, Apache Beam, or Apache Airflow. TensorFlow Extended is sort of a funny setup. It's more than a library, but not enough for a framework because it runs within the TensorFlow ecosystem. It is somewhere in between because it contains a number of libraries which can be used as standalone libraries. A great example is TensorFlow data validation or TensorFlow model analysis. Those tools can be used to analyze machine learning models and even models which aren't produced through the TensorFlow framework. So TensorFlow data validation works great together with PyTorch models or scikit-learn models. But then each of the libraries also provides the functionality to components, which then can be tied together in pipelines, which we then would call through the TFX library in that case. Through TFX, we can express, as I said earlier, we can express our complex pipelines, and then we can run those pipelines agnostic of the orchestrator. So we can swap out the orchestrator under the hood, and we can say, hey, today we run it in Apache Airflow. Tomorrow we run it in Kubeflow pipelines if we need to. At Digits, we're running Kubeflow pipelines for various reasons. But for example, if your company has already invested heavily in Apache Airflow for existing ETL processes, then using the infrastructure is easy to do with TFX. You can use the orchestration for Apache Airflow. Or sometimes companies are already using Dataflow or Apache Beam. No problem, you can use this as an orchestrator. TFX, all the components in the TFX ecosystem have the same consistency, so that they consist out of like 3 parts: the driver, the executor, and the publisher. The driver loads all the references from a metadata store, and the publisher publishes all the references which are coming from the components, like let's say a manipulated data set or some annotation to the machine learning model or something like this, that the publisher will then write those information back to the metadata store. So as a developer, I don't have to worry about like, where do I track all my information? It is all being handled by TensorFlow Extended and happens under the hood. This doesn't need to be defined. Let's say, as an example, in the Kubeflow Pipelines SDK, where we have to sort of like make sure which artifact is being tracked and which one isn't. Everything which goes in and out of those components is being tracked in the metadata store, and that's super useful for scenarios where we want to do artifact tracking, or we want to track the model lineage and maybe retrace artifacts which have influenced the model in a certain way. And then those metadata stores, they run on like standard relational databases. In this case, it's in SQL or a SQLite database. So then why should people think about TFX beyond their machine learning models? First of all, as you probably saw, is like you can express the entire machine learning lifecycle through components, and you can abstract that through simple Python code. Most data scientists working in the Python environment anyway. Here you can express your machine learning pipelines as Python code, and that Python code can then get converted into YAML files for your Kubernetes setup if you want to use Kubeflow pipelines. But you don't have to write any YAML code. You stay in the Python ecosystem. The orchestration, as I mentioned, is agnostic from the underlying runner, so you're super flexible. There's even a chance you can write your custom orchestrator if you're really into this. If you're running something which is not currently supported, you can also write your own support there. It has the metadata as its core. There's amazing applications coming out of the metadata. Model cards is one of the applications you can automatically generate, like information pieces for non-data science stakeholders of your machine learning models, if you want to communicate this to product managers or designers. If you have a need for custom components, TFX is easily extendable. We're using custom components pretty heavily at Digits here. We have a couple components to annotate our machine learning models before we push them out. And the implementations are super straightforward these days. It's really great to see how easy that is. And then TFX enables you to distribute the data in your machine learning pipeline quite easily. So each data-heavy component is using Apache Beam under the hood, and you can define Apache Beam in such a way that it would outsource all the data-heavy stuff to Apache Spark or Apache Flink, or if you run in the Google Cloud ecosystem, you can then outsource all the data-heavy manipulations to Dataflow. How does it look like in a real-world scenario? So here's basically the definitions of a few components. You basically create for each component a Python object. We would ingest our data. In our case, we use BigQuery pretty heavily to load our data from our repositories. Basically, we define a query. We load the data from BigQuery. Something which we have left out here is like you can specify specifically how the data is supposed to be loaded. You can perform splits here. You can split the data into training and validation sets. You can read from spans. You can read. You can shuffle the data. There's like tons of configurations you can perform in your pipelines. The data can then be consumed by a statistics component, where it's generating basic information about your data set. The statistics are then being passed into your schema generator, which is then looking into what features do we actually have. And it would tell you if, for example, a feature has dropped completely, or a feature has changed from a dense to a sparse feature. And then those information are being consumed when you transform, or when you perform the feature engineering in the transform component. And again, everything is like you define your entire pipeline here through code. We would continue this definition here where we have left out with like a trainer component, evaluator component, a pusher component, and that would basically your pipeline. And then you perform, or you create a pipeline out of this as another object, and that object can be converted into whatever platform you want to run it on, whether it's Apache Airflow, Beam, or Kubeflow pipelines. And in the case of the former two, you would basically immediately execute it as a Python script. If you convert it to Kubeflow pipelines, you would convert it to a YAML file, and that YAML file could then be executed on your Kubeflow environment. We would like to just highlight a couple TensorFlow frameworks here, which are extremely useful in our environment at Digits. And one of them is the TensorFlow data validation library, which we mentioned earlier. It is very easy to use, and it allows us with just 2 lines of code to get a basic understanding of our data sets. And that is a super great tool to just get a project started. Let's say we have a project idea, we have a data dump, and we want to figure out like what features could be potentially used for our machine learning models, which ones are dense, which ones are sparse, what's the distribution, do we have a certain long tail of classifications, etc. That's something you can do with data validation. It works as a standalone project, as I will show you here in a second. But you can easily integrate this into your pipelines as well. Here's an example for a standalone project. So if you would run this in a Jupyter notebook, you can load your data from various sources. It supports, like as it's shown here, CSV. You can use pandas data frames. You can use TF records. There's probably by now a bunch of other entry points as well. And then you just call the method visualize statistics, and it just does all the basic statistics under the hood for you. You can then load a second data set, and that could be your evaluation data set if you want to compare it with your training data set. And you can call the visualization method again, specify which data set is on the left and the right side, and then you basically overlay those 2 data sets, and you would see the delta between them. And when we want to train machine learning models and we want to evaluate them consistently, we want to make sure that the distributions in our features are roughly the same in our training and a validation set. And that is something you can easily confirm with these 2 lines of code here, and get a visual representation of that matching of the 2 data sets. And when you run those methods in your notebook, it creates an iframe. You get all the information. It splits out the numerical with the categorical features. You see the basic information. It's probably not rocket science for any statistician, but to get a data science project up and running, it's extremely useful. We even see like little plots and charts, which help us understanding what's the data distribution for the particular features. Another library from the TensorFlow ecosystem, which is extremely useful before we train machine learning models, is TensorFlow Transform. And I think it's the most underrated TensorFlow library in the ecosystem. It is extremely useful because we can express our feature transformations as TensorFlow ops. And you might wonder, why do we need to do this? It's so much quicker to do this in TensorFlow, so much quicker to do this in Pandas or in scikit-learn. TensorFlow is sort of always finicky when sometimes you can use ER execution and sometimes you can't. The whole point of that is if you express it as a graph through TensorFlow ops, it is very straightforward to perform distributed processing on it because you know the dependencies within the transform operations. And then you can, because you basically have a transform graph, you can then use Apache Beam to distribute the pre-processing of the data. as wide as you want. The cool thing is with TensorFlow Transform, it gives you two outputs. One is a transform graph, and second, it gives you the transformed input data. And so from the transformed input data, you can accelerate your training because you don't have to do the feature conversions with every epoch. So you do it once, and it speeds up your training. The fact is that you get a transform graph opens the opportunity that when you export your machine learning model, you can combine the transform graph with your machine learning model and export a single graph. And so when we deploy machine learning models at Digits, we only deploy a single artifact that contains all the pre-processing steps with our trained machine learning model, and they never get misaligned. So for example, if you have like a feature you want to normalize and you want to figure out what's the minimum and the maximum of your feature, TensorFlow Transform does it automatically. It goes through your training data set. It figures out what's the minimum, the maximum. In a second step, it normalizes all the features. And then when you perform the same transformation on your validation set, it will use the learned minimum and the maximum. So automatically, a lot of those misalignments, which sometimes get messed up in data science projects, are completely not existing anymore because TensorFlow Transform takes care of that. How does it look like in a real world scenario? Here in this case, this would be like a standard implementation for a simple like text classifier model. We have a raw string, we split the raw string, we convert the tokens into vocabulary, and then we only want to preserve the top K tokens or vocab size tokens. And then based on those tokens, we create TF-IDF vectors. Here in those, 3 lines of code, that would take a little bit more of Python code if you write this A from hand, and it would bring in a much more complexity in terms of what needs to be transferred into production environments, what needs to be sort of like, there's a lot of coordination would be needed if we perform some of those transformations in backend code before we infer from our model servers. And here we have the great opportunity to push a lot of business logic into our machine learning models to make the deployment as simple as possible. Then we train our machine learning models. And once we get the models back and they're sort of evaluated through the pipelines, we can then take a look at the model with our internal tooling. So internally, we have developed tools to do unit and integration tests. And we take a look at a quantitative and a qualitative look at the model. So we run it against the baseline, we run it against other data sets we have preserved, and we make sure that that the model runs in parameters we have defined beforehand. And to do that, we use the technique what Joe was mentioning earlier, that we split our data sets into a data set and a test set. And that test set is put aside before we even start our machine learning pipelines. In the pipeline, we then split the data set again into a training set and a validation set, and we run with that second split through our entire pipeline. And then when we want to do testing after the model is being exported from the machine learning pipelines, then we use that test set. And these days, we have the great opportunity of using additional tools, like, for example, the what-if tool or the language interpretation tool. And for that one, to use it correctly, we would need a fourth or a third set, depending on where we start counting, so that we're not testing with the wrong data set. So we need to set aside another data set in order to do correct testing. So when everything checks out, we can then start talking about how to deploy our machine learning models. And at Digits, we use TensorFlow Serving. TensorFlow Serving is really great because it does exactly what it's supposed to do. It deploys a machine learning model. And it doesn't do anything else. It doesn't do any traffic routing. It doesn't do any like A/B testing. It just is high performance, or it's high performant when it comes to serving those machine learning models. And the great thing about TensorFlow Serving is it runs on C++. It takes this entire global interpreter lock problem, which we have in the Python environment, out of scope, and we don't have to deal with this anymore. We deploy TensorFlow Serving through Kubernetes, and we have the policy that we run 1 pod per model, or 1 model per pod. So that means when we have a new model version, we don't hot swap models under the hood. We basically deploy a new config map for our pods, and then redeploy those pods. And Kubernetes then takes care of the phasing in and phasing out of new model versions. TensorFlow Serving is extremely great because we have that great feature of using mini batches. So this is a great tool if we have like endpoints, especially user-facing endpoints, where the load is sort of unpredictable, but you still want to use your hardware as efficient as possible. We can define mini batches, and we can wait for a given amount of time or until a certain batch is full, and then compute everything on block. We don't do like single round trips for single requests. And it also integrates really well with the what if tool. The what if tool can connect directly to TensorFlow serving endpoints and use them to do the model validation or model testing. And here's a brief example of like how a deployment file for Kubernetes would look like if we would deploy like a simple machine learning model in this case. If you deploy TensorFlow serving, you do not have to build your custom containers or custom images. You do not have to put your models inside of an image because first of all, Google provides you pre-built container images or serving images, which you can load with the latest TensorFlow version under the hood. And then you can always load the machine learning model from any cloud bucket, whether it's GCP or AWS, doesn't matter. You can load it from cloud buckets. There's one line missing here, which didn't fit on the slide anymore. But if you load from a cloud bucket, just a little hint, you should reduce the amount of polling on those buckets. Otherwise, you pay for every list request. If you don't update your models every second, you might want to drop it to like a minute or every 2 minutes. It's totally fine. But you could also, on our end, we have disabled this totally because we deploy new pods with new model versions. If you want to support the hot reloading, maybe go for 60 seconds or every 2 minutes. So with that, I think we stepped through the entire end-to-end data science process here, and I hand it over to Joe.
All right, so hopefully at this point, you have also arrived at the conclusion that investment in ML engineering definitely pays off. You know, for us, it cuts down the time to first model from weeks to days. It's super easy to onboard a new data engineer, like with little or limited experience in ML, you know, I'm thinking about myself to be productive in this process with the tooling around it. And it's easier for your data scientists and and ML engineers to debug the problems with the model so that you don't have to pull your hair out about, you know, what about the data that has shifted. And we have like a very streamlined process for producing models that can be repeatable, reproducible, and also can be operated at scale. So we are Digits and we are hiring. So if you go to digits.com, you might see 2 open recs, one for ML engineer and the other for software engineer. So Digits, we actually have been a fully remote company like since inception back in May 2018. So we have really colleagues across the continental United States. And myself and Hannes are in West Coast, but we do have people elsewhere. So let us know if you're interested in working with us. That is all. Yeah, thank you so much.
Well, a huge thank you to you both, Joe and Hannes, for excellent talk. We have a few questions that have come in. So let me switch back to our video feed here. Alrighty. So one early question that we had. So earlier on in the presentation, one of you mentioned that you're predominantly using gRPC endpoints for model serving. For a lot of companies who are, you know, more accustomed to working with RESTful APIs or, you know, God forbid, even SOAP APIs, could you speak to sort of what that decision looked like for Digits in terms of, I know TensorFlow exposes that sort of natively the gRPC interface, but sort of the pros and cons that you evaluated as you're making that choice in how to serve your models?
Yeah, maybe I can speak to this and Hannes can chime in. So just based on our like past experiences, we were like the team used to work at Google, so we were fairly just comfortable with using like gRPC as opposed to like a JSON as a data transmission format. Um, and so we already have a lot of infrastructure built out for it. We operate our a few internal services in Google Cloud, so they are all like gRPC services. So I guess like the short answer to that is we already have the stack built out for it. We didn't actually go through the entire process of like laying out the pros and cons for using REST versus gRPC. And obviously for REST, like it's more familiar to most folks in the engineering world. And the cons would obviously be like you are dealing with a much larger payload. Yeah.
There's a slight benefit of using gRPC when it comes to model serving. If you, like, for example, TensorFlow serving provides two versions of endpoints. It provides a REST endpoint and a gRPC endpoint. You might see some speed differences if you switch over to gRPC. In the case, if you have a lot of features of various dimensions. The reason is if you use a REST endpoint, the JSON blob you submit to the endpoint doesn't really have any type annotations. And so then on the server side, the TensorFlow server needs to figure out what types are being submitted. It does some type checking there, or the value checking in this case. And on the gRPC side, you don't have to do this anymore. The client already converted everything in the right formats, and that speeds up the model inferences on the server side. But that is something you would see at like higher throughputs and high throughput values. So if you have like a small machine learning model server, you might not see the differences there.
That's great. Thank you. All right, so our next question is around model testing. And this is, I love this because this is something that never gets talked about. So you mentioned model unit testing as part of sort of the overarching ML lifecycle at Digits. Can you speak a little bit more to sort of what it looks like, what you're looking for, how you approach those unit and integration tests?
Yeah, so there's multiple dimensions. So first of all, in a unit test, we want to make sure that the model performs as sort of like as intended, and that we do this by having what we call a baseline. It's a very small data set which humans have curated. Sometimes like 3 data scientists sit on a single screen and review every single data record. But then we have data samples where we're absolutely certain that the label or the result is correct. And then we use this in our unit tests to make sure that if the model performs or if the model predicts something, we can then see does it roughly align with what we had expected. We also do this over a much larger data set, which isn't that highly curated, but we see this more like on a quantitative level of like, do we see a trend going somewhere, or does a trend somewhere in that direction? But that again becomes more like an integration test, because in this case we sort of like have to go through a bigger pipeline. We go through we go through a larger set. And then we sort of like take a look at like what's the confusion matrix for classification problems, for example, and we say, does it still align with what you had expected? The thing is, when we do the integration tests, we have this problem of like, what's our baseline, what's our ground truth, and that is often sort of like the tricky point. So that's why we have a very small, highly curated data set, and then we have a larger data set where we could potentially see trends, is like a model drifting in terms of like the predictions.
That's awesome. Thank you. All right, so our next one looks like a 2-parter here. Okay, so first part being both around TensorFlow extended ecosystem. So first part is, are there any resources you would recommend for data scientists who want to work with TensorFlow extended components, but with non-TensorFlow models? And as a follow-up, sort of, you mentioned some custom components that have been written at Digits for model annotation. So can you speak to those a little bit in terms of sort of what they do and how they're used in part of the larger model serving ecosystem?
Okay, so the first question, correct me if I understood this wrong, understood this correct. The first question was like how to use TFX in the context of non-TFX models.
Yep, exactly.
Okay.
Or are there components that can be used outside of TensorFlow?
Yeah. So there's currently A couple months ago, a working group was founded between a variety of companies, and Digits was one of the founding members. And we focus on providing examples and components for the TensorFlow ecosystem or TensorFlow extended ecosystem. And one of the very first projects, I think Google provided this, is an example of how to use scikit-learn with TensorFlow extended. So they're going through the entire example of running a pipeline, not with a TensorFlow model, but with a scikit-learn model. So if you take a look for the special interest group called SIG for TensorFlow extended, you can find more information. There's a GitHub repo, and I think that example should show up in the next few weeks if it isn't already online. And for the second question, what do we annotate? This is a little bit like internal IP, but I can say so much that when we deploy machine learning models, we annotate them in such a way that we, independently where we deploy our machine learning models, we know where that model was generated and what happened to that machine learning model. And this basically ties everything back. So we don't have to, the model knows the metadata in itself. I don't know if that makes sense. So we don't have to carry like a second file or anything. We deploy the machine learning model. We can go to TensorFlow serving and ask a couple of questions, and then we get enough information out that we know, okay, this model was trained by this person at this date, and so on. So that's something we do by annotating our exported models, if that makes sense.
Yeah, no, that's great. Thank you. So I'm not seeing any new questions coming through in the feed here. So I'll give it another few seconds here if there are any stragglers. But otherwise, thank you again, Hannes. Thank you, Joe, for an amazing talk. Again, digits.com. They're hiring. Folks, check it out.
Thank you, Christopher. Thank you, Braden. Thanks for having us. It was great to be here.
Thank you all. Thank you for having us.
Absolutely. Thank you, guys.